We're good. Awesome. Thank you so much for being here. My name is Juliana García-Mejía. So yes, that's a very Latin American name. I'll tell you all about that in a second. But first I wanted to thank you. I wanted to thank you for coming here, spending this time with me. Time is the most precious resource that we have. And I'm actually going to take this time that you've given me to tell you all about the search for Earths outside of the solar system. The search for planets just like our own, but that are just a little too far for us to just get there by a spaceship. But before I do, I wanted to actually take the opportunity to tell you a little bit about who I am, because I keep getting asked this question here in the audience. I had the pleasure of talking to some folks, and a lot of them were like, so how did you get into this line of business? So I'm actually going to tell you the story, but actually my story starts like all of your stories 13.8 billion years ago. When the universe experiences accelerated expansion, following that expansion, we have the formation of hundreds of billions of galaxies. And these galaxies all came from those little cribs you see over here. This is the formation of the very first stars. And then all of those stars that you see here turned into galaxies. And amongst the billions of galaxies that were formed, only one is the one where we found ourselves emerging. That is the Milky Way. And within the Milky Way, there was one star that formed. And as that star formed, because the trash of some is the treasure of others, out of all that gas and dust around those stars were formed the solar system planets. So Mercury, Venus, Jupiter, Mars, and the Earth. But at the beginning, this environment, you can imagine, was absolutely chaotic and infernal. And so our Earth was actually being constantly bombarded by comets and asteroids. And actually, it was one of those collisions of a giant asteroid that we think was the size of Mars that gave rise to the formation of the moon, as I'm showing here on the video. And then after the formation of the moon, the Earth was absolutely hot. The surface was melted. It was a total, imagine like a volcano planet. But then out of the depths of that Earth, water started emerging. And the Earth started cooling. And then all of a sudden, as the Earth cooled, we still don't know exactly how it was, but life emerged. We don't know if it was in the depths of the ocean. We don't know if it was in little lakes, but we just know that this is the time when life first formed, the very first cells. And those cells were very simple at the beginning, but they started generating oxygen. Oh my God, they started generating oxygen. So the Earth filled up with oxygen, but it turns out that oxygen cools the Earth. And so the whole thing actually froze over, like you're gonna see in a second, and then it unfroze again. And then all of a sudden, when it unfroze, life became so much more complex. And then after it became more complex, we had a lot of diversity emerge, and then we had amphibians leave the waters. We had the formation of woods and reptiles. The dinosaurs took over. Then they became extinct. And then we had the emergence of the mammals. And finally, after this whole very long story, us. So this is how we all got here. And then another 200,000 years have to pass. For me, isn't that funny that now I'm going to be talking about myself? For me to be born to a Colombian family in 1995. And not just any family, a crazy family, a very eccentric family, in the best possible way that one can use the word eccentric. On the one hand, I was born to the owners of the first Olympic gym in Colombia. It was called UROS. It doesn't exist anymore, unfortunately. And it was founded by my grandmother, a woman who was born before her time, my very eccentric uncle who built all the machines in the gym from scratch, and my mother, the most charismatic woman you'll ever meet. That's her over here in blue with the curly hair. And I spent my days following this guy around with the big belly, seeing how he built those machines and how he built this gym from scratch, along with my mom and my grandma. And then on the weekends, when we got tired of all this movement, I actually had a chance to go to my family's coffee farm. This is on the outskirts of the city where I was born. This is called Concordia. Now, of course, the whole thing that you're seeing is not my family's farm. I'm taking that picture from my family's farm. You can see virgin forests here in the foreground. You can see the rows of coffee. And I'd spend my weekends playing with my cousins. You can see here I'm the little blonde girl in the picture. We would play safari. This is us after we arrived from a particularly exciting day. And I learned how to pick coffee. The coffee beans that you see, the coffee cherries that you see in the tree. But my favorite part about this whole crazy childhood was actually when my uncle, the same guy I was just telling you about that built all those machines, would sit us cousins down after a long day of staying up at the farm, and he'd tell us all about the universe. And he'd ask us questions like, do you know whether life exists in other planets? Do you know whether the moon is important for life here on Earth? Do you know how life first emerged on the Earth? Do you know if there's life elsewhere? So these are all the questions that I grew up around, and I was just absolutely thrilled. I paid a lot of attention to my uncle, and so I decided that I wanted to dedicate my life to bring human beings closer to the stars. But if you know anything about Latin American culture, is that in families like mine, you can only be one of four things: business owner, lawyer, member of the clergy, or engineer. So I interpreted my love for the cosmos through aerospace engineering. And I decided I wanted to become an aerospace engineer. I wanted to build rockets to bring humans closer to the stars. But how are you going to do that in a country that doesn't even have a space agency? So I was actually lucky enough that my parents had the foresight to have me be born here in the US so I could have access to all of the educational opportunities in the US. So I declared that I wanted to go to the Air Force Academy to study aerospace engineering. I'm an only child, so you can imagine how that one went. And in any case, my parents said, you know what, we're just gonna allow you to go to Columbia, to the US and study there. And I had a wonderful family. This is my uncle Alvaro and his wife Laura, and they took me in Gainesville, Florida. I don't know if many of you are familiar with the town, so that I could finish high school and then attend college. And as luck would have it, I got into Harvard for my undergrad. So cool. Thank you. But wait, there's a problem. Harvard didn't have aerospace engineering. What? I was like, you know what? Whatever. It's Harvard. Actually, let's just go. Let's give it a shot. So this was how I spent my entire days while I worked. My entire days or nights. You can see in the clock that it was almost 1 a.m. I spent it with my two friends, just trying to figure out problem sets, trying to go through all of these classes and these exams. And it was a really difficult time. It was a really difficult time. I became really discouraged. I didn't know what to study. Turns out I started taking engineering classes and I hated them. They were such a drag. I was like, this is not it. And so when I went, I said, you know what? What I really liked were my conversations with my uncle. What I really liked was to learn about astronomy. So let me just take an astronomy class, see how that goes. And so I took an astronomy class with Professor John Johnson. And one day he asked me, Juliana, what do you want to do with your life? And I said, well, I'm just taking this class for fun. I actually just want to be an aerospace engineer. And he said, have you heard about astronomical instrumentation? Who here has heard about astronomical instrumentation? Oh, we're lots of hands up. I at the time had no idea, one, that you could be an astronomer for a living. That was the crazy, most outlandish idea ever. Number two, I didn't know that you could build instruments for astronomy for a living. So, oh my God, all of a sudden, I found my calling. I found the one career path that would combine all that hardware knowledge that I had learned from my uncle in that gym, all that adventuring that I had done in my farm in Colombia with my cousins, and brought them all together to build the next generation of instruments and telescopes, but not just to answer any question, but to answer a very particular question. Is there life elsewhere in the universe? And that is what brings me here to tell you all about the story of how it is that actually astronomers go about answering this question, because many astronomers actually think there's many different ways to answer how it is that there's life, whether there's life elsewhere in the universe. As a show of hands, I would just love to know who here thinks that there's life elsewhere in the universe. Wow. And who here doesn't think that there's life elsewhere in the universe? I raised my hand because I actually agree. I think it's actually so incredible that there's life, but we're not going to get into that. We can get into that in the Q&A. In any case, so how does that work? So as astronomers, there's a very particular way that we approach this question, right? So as astronomers, what we're trying to figure out, first of all, is if there's life elsewhere in the universe as we know it on Earth. And as it turns out, that whole story I told you about the history of how we all arrived in this room from 13.8 billion years ago to now actually has a very specific purpose, and it's that it shows that there's one characteristic about the Earth that is absolutely important, and that is its size. It turns out that for the life to emerge as we know it on Earth, the planet had to be the size that it is. So as astronomers, the first step in this quest to search for life is actually to figure out whether there are planets that are about the same size as the Earth out there. And those planets we call exoplanets. We call them terrestrial exoplanets or Earth-sized planets. So that's how I'm going to be referring to them today. So how are we going to find them? So I'd like you all to put on your astronomer hats here for a second and help. Let's see if we can find them together. So let's imagine that there's a star, right? And we want to figure out if there's a star orbiting this planet. Any ideas of how we can find it? What was that? Look for it to disappear.
Yeah, look for it, something to dinner.
Oh, I see some folks already know about this. Amazing. So yes. So what we do is we actually stare at that star for a very long time. And we take pictures of it. We take pictures and pictures. And if at some point the amount of light that we're getting from that star dims, it might be because a planet has passed in front of it. So all that we're looking for the whole time that we're doing this study is we're taking a picture here, doing this plot I'm showing over here, taking pictures and pictures, measuring the amount of light that we're getting from the star, the amount of light that we're getting from the star, and as that planet passes in front of that star, there's a dip in our plot of light. And that is the dip that we're at, right? And already with this method, this is what we call the workhorse method of astronomy. With this workhorse method, we've actually found 5,000 planets outside of the solar system, but within our Milky Way galaxy. 5,000 planets. And they're absolutely incredible and diverse. Let me show you a few examples. So we're here, I'm showing our Venus and Earth. Of course, these are graphical interpretations. These aren't actual pictures of those planets. But we found some of the smallest planets we found are actually about the same size as Venus. That's Kepler-20 here on the left. And as large as the Earth or a little larger. That's what we call Kepler-20f over here on the right. So we found some, very rare, but we found some planets the size of the Earth. We've also found systems that are like super tight. So imagine, so we have Mercury. Mercury is the closest planet to our sun in our solar system. We found systems that have 1, 2, 3, 4, 5 planets interior to their sun. So if we were to put Mercury in those systems, actually all of these 5 planets here would be even closer to their sun than Mercury is. Incredible. How can that system actually survive if those planets are so close to their sun? We've also found incredibly large planets, even larger than Jupiter. An example here is HAT 67b. There's an enormous diversity of planets that we found, but statistically speaking, perhaps the most surprising thing that we found amongst this population of 5,000 planets is that the most common ones are not represented in our solar system. So what do I mean by that? We have Neptune. We're familiar with Neptune, yeah? We have the Earth. We're hopefully familiar with the Earth. It turns out that the most common type of planet outside of the solar system is a planet that is between the size of the Earth and Neptune. There's no such planet in our solar system. What's up with that? Could it be that our solar system is absolutely unique, and therefore the things that happen in our solar system, such as the emergence of life, are absolutely unique? Or could it be that the eyes that we have on the sky are actually not powerful enough to show us the real population of Earth-like planets, the ones we are actually after? So when I started my PhD, this was the state of the field. We had We have just discovered that these planets that are not in the solar system were all over the Milky Way galaxy. And we were having a really hard time finding Earth-sized planets, which again are the ones that we really, really want to look for if we want to search for life. And so amongst this huge diversity of solar systems, I decided that I wanted to spend my PhD looking for these Earth-sized planets. But what's the challenge? The challenge is that statistically speaking, we actually think, as of 9 years ago, we already know that statistically speaking, there should be 1 to 3 Earth-sized planets for every single star you see in the galaxy. So we should be full of Earth-sized planets. So why are we not finding them? Where are they? What's going on? Any ideas? Time. That's a really good point. We have limited telescope resources. So how are we gonna know if we're actually looking in the right way, in the right place, at the right time, right? Because we have to catch those planets as they're passing in front of that star. So it seems like a very difficult problem to solve. Any other ideas?
I think we could be off by a couple billion years.
That's true. Exactly, we could be off by time, and so maybe those systems will eventually have planets like the Earth, but they just haven't formed yet. They haven't had a chance. So it seems like a really difficult problem to tackle. But nonetheless, there's people like me who want to spend their entire lives, dedicate their lives to build these instruments. And when I started my PhD, I realized that one of the problems we had was we didn't have enough resources. We didn't have enough telescopes that could actually deliver the precision, the quality of data so that we could identify those Earth-sized planets. So what is it that's so difficult about finding Earth-sized planets? So we go back to this whole thing of the transit method, the dip method I was telling you about. So if we're looking for an Earth-sized planet around the sun-like star, that's the depth of that dip. It's tiny. There is no telescope in the world right now that can deliver that type of precision to find those Earth-sized planets. So if we really wanted to look for an Earth-sized planet around a sun-like star, like literally like our own solar system, we just are out of luck. We're gonna need a few $1 billion to do that. Definitely way more than my PhD advisor wanted to give me to graduate. But we can actually cheat a little bit by looking for those same Earth-sized planets around the smallest and most common type of star in the galaxy. We call these red dwarf stars. So the exact same planet, as it passes in front of that star, because that star is way less bright, will actually generate a dip that is 100 times deeper. So it's the same planet, just around another star, a red dwarf star. We can talk about the implications of that if you want. But the point is that we can cheat a little bit and make the problem 100 times easier, literally 100 times easier. So that's exactly what I set out to do. In my PhD, I inherited a very old telescope called the 2-mast telescope. It's located right around Mount Wrightson. Some of you might remember this view. And the telescope was actually built the same year I was born, 1995. But then the telescope was actually left completely abandoned for a decade. So by the time I took it over, it was completely mothballed. So I decided to turn it into an ultra precise, super powerful facility dedicated specifically to look for those Earth-sized planets around those red dwarf stars. So how is it that we do this? I told you I was an instrument builder, and I have to be true to who I am. So I'm actually going to take you on a journey through the telescope. So we're actually going to go through the telescope, go inside of the telescope, and see what it is that happens when light from those red dwarf stars reaches the telescope. What it is that makes it special. So at the end of the day, what is a telescope? A giant bucket. It's just that instead of collecting water, what we're actually doing is we're collecting light. So in my case, the telescope's primary mirror, the bucket that's collecting light, is a 51-inch primary mirror. And then what I spent my entire PhD doing is building an instrument. This instrument is the instrument that actually will take all that light that bucket has collected and process it to turn it into data where we can actually look for these planets. So what's special about the instrument? Well, it I'll tell you in 1 second, but first I told you I was gonna take you on a journey through the telescope. So let's imagine that we have light coming from one of these stars. So this light has traveled literally in the closest of cases, this light has traveled like 12 light years. So it's far, it's like billions of kilometers. That light has had to travel billions of kilometers to reach our primary mirror. And then after that light reaches that primary mirror, of course it's a mirror, it gets reflected up to this secondary mirror. And then that secondary mirror will continue to focus that light and pass it through a primary mirror hole. And then that primary mirror hole allows the light to reach the instrument. And the first thing that that light sees when it gets into the instrument is a custom filter. So this is a filter that I designed. It's one of a kind, and it actually, what it does is it inoculates the observations, the light, from the worst enemy of ground-based astronomy. What is the worst enemy of ground-based astronomy? Light pollution, the atmosphere. So, I mean, I wish I could take the atmosphere away, but then we'd have a billion other problems to figure out. So what this filter actually does is it gets rid of all the issues, or as many of the issues as we can, that are associated with ground-based astronomy, light pollution, the atmospheric effects, the water in the atmosphere. It's like a miraculous filter, so to speak. And then after that light has been filtered, it passes through a set of 4 coded optics. And these optics, what they do is they increase the field of view of the telescope. So that's not unlike how the cameras in your iPhones in your pockets allow you to take those wire images. That's exactly the same thing that we're doing here, just a little bit bigger. And then after all of that light has passed through the optics, it finally makes its way to what we call the CCD chip. This is just a piece of technology that allows us to turn all of that light we're receiving into data, the data that we actually want to analyze to see if we can find these planets. So my amazing team and I have already spent countless hours building this instrument in the lab. Oh no, wait. No. All right, let's play this. Spoiler alert. So my amazing team and I have already spent countless hours building this instrument in the lab. So then after we built the whole thing in the lab, we had to pack the whole lab in Cambridge, Massachusetts. That was where I built it. Then we brought it to Arizona. And then you can see us here in the midst of packing, installing the whole thing. Then we had tons of problems, so I had to stay up and play with the telescope, align the mirrors. You're about to see me aligning the mirrors. You just saw me aligning the mirrors, solving all sorts of hardware and software problems until finally one beautiful night in the fall of 2021. I got my first light image. This is the first light image of the telescope. Woo! Amazing. So I spent 6 years, 4 years building this thing. I had no idea if it was gonna work. I hoped it did, but many things can go wrong. So it was absolutely miraculous to get this first light image. So to that young kid that I was telling you about in Colombia, I played with her uncle and learned all about gym hardware, and then looked up at the sky from her farm. This first light image was a dream come true. Can you imagine? But to the astronomer of today, this is just the beginning. When I see this image, I actually see a million problems. I see a million ways in which we can improve the telescope, but nonetheless, since the fall of 2021, we've been gathering data and data and data and more data and more data. And what have we found? There's a dig. That's a known planet, by the way, so it's boring. We have found nothing, absolutely nothing. We've been solving hardware issues, and we've been staring up at the vast sky and realizing this is just a really difficult problem that we're gonna have to crack. But thankfully, we have 10 more years with the telescope, and we have tons of sky to observe. And that's what I'm gonna be doing for the rest of my postdoc, and what I hope my students will continue to do as I become a professor one day. So I guess to finish up, I really want to hear your questions. I hope you have a lot of questions. I just want to say that the one thing I know for sure from my search for other Earths is that this little dot right here, this is the Earth as seen from Saturn, is a very special place, absolutely miraculous place. There's seems like there's really, at least in the vicinity of the sun, nothing quite like it. So we really got to take care of it and enjoy the paradise that we were so lucky to be born in. It's absolutely miraculous that your brains and mine are coming together here after 13.8 billion years to talk about the universe and the search of other potential brains out there, whether those exist or not. And finally, I just wanted to say that this is something that I don't do in isolation. I do it with a wonderful team of astronomers and staff and technicians and machine builders. And these are only some of their faces. This is their staff at the Fred Lawrence Whipple Observatory. And we cannot wait to see your faces. Come and visit all these instruments that are making possible, making the study of the universe and all of its wonders possible. So we have a lot in store for you when that science center opens. Thank you so much. Keep working up.